Hello, have a good day. We are going to do the numerical questions of chapter number 1. I am going to solve the questions from my personal book. You guys will have to solve the drill problems of engineering electromagnetics by William Hatt, chapter number 1. That is your homework. So please do all the drill problems of chapter number 1 from the recommended book of William Hatt. I recommend the 5th edition of this book for your course. So let me do example number 1.1. In example number 1.1, we are going to consider two vectors in rectangular coordinate system. We shall add these two vectors. We shall compute the scalar product of these two vectors. We shall compute the vector product of these two vectors, and we shall consider the angle between these two vectors. Okay. So let us consider these two vectors in the rectangular coordinate system. This is a vector in the rectangular coordinate system. This is a three-dimensional vector, and this three-dimensional vector has got three components: 3ax plus 2ay plus 2az. We consider a three-dimensional vector b in the rectangular coordinate system. B is equal to ax plus 3ay plus 4az. So we calculate the sum of these two vectors. We know that the addition of two or more than two vectors results in a new vector quantity, and vector addition obeys commutative law. So a plus b will be equal to 3ax plus ax, that is 4ax, 2ay plus 3ay, that is 5ay, 2az plus 4az, that is 6az. So the resultant vector is a three-dimensional vector, which is 4ax plus 5ay plus 6az. Now we are going to calculate the scalar product of these two vectors. We know that the scalar product of these two vectors results in a scalar quantity which is equal to ax bx plus ay by plus az bz. So this is how we calculate the scalar product of two vectors in the rectangular coordinate system. So let us calculate the scalar product. We have 3 into 1 plus 2 into 3 plus 2 into 4, and that results in a scalar quantity which is 70. We calculate the cross product of these two vectors with the help of this determinant. So in the first row we have the unit vector ax, the unit vector ay, and the unit vector az. Ax is 3, ay is 2, and az is 2. Bx is 1, by is 3, and bz is 4. So we expand this determinant, and the expansion of this determinant results in a new vector, and this new vector is a three-dimensional vector which is 2ax minus 10ay plus 7az. We calculate the magnitude of vector A. So the magnitude of vector A will be equal to under root square of the x component, which is 9, plus square of the y component, which is 4, plus square of the z component, which is 4 as well. So the magnitude of vector A turns out to be 4.12. We calculate the magnitude of vector B, and the magnitude of vector B will be equal to 1 under root 1 square plus 3 square plus 4 square, that is under root 1 plus 9 plus 16, and that is 5.09. We know that A dot B is equal to AB cos theta. So we calculate the angle from here. The angle between these two vectors will be equal to, theta will be equal to cos theta A dot B theta will be equal to cos inverse A dot B divided by AB. So we know that A dot B results in 17, and the magnitude of A into the magnitude of B results in 20.97. We simplify this equation, and this equation results in the angle between the two vectors A and B, and the angle between these two vectors is 35.9 degree. We go for example number 2. Consider the two vectors in rectangular coordinate system. Find the angle between A and B with the help of vector product. So we consider these two vectors. These two vectors are in the rectangular coordinate system. They are three-dimensional vectors. We want to calculate the angle between these two vectors with the help of cross product. So let us calculate the cross product between these two vectors first. We calculate the cross product between these two vectors with the help of this determinant. We calculate A cross B with the help of this determinant. So in the first row, we have the unit vector Ax, the unit vector Ay, and the unit vector Az. Then in the second row, we consider the x component of A, which is 3, then the y component of A, which is 4, then the the z component of A, which is 0. In the second row, we consider the x component of B, which is 4, the y component of B, which is 3, and the z component of B, which is 1. We expand this determinant, and the expansion of this determinant results in a new vector. This is a three-dimensional vector, which is 4ax minus 3ay minus 7az. This three-dimensional vector will be normal to the plane containing A and B. We know that the resultant vector in case of the cross product is always normal to the plane containing A and B. We calculate the magnitude of the resultant vector. So let us calculate the magnitude of the resultant vector. The magnitude of the resultant vector will be equal to under root 4 square, which is 16, plus minus 3 whole square, which is 9, plus minus 7 whole square, which is 49. So the magnitude of the resultant vector turns out to be 8.6. We calculate the magnitude of A. We know that the magnitude of A will be equal to under root square of the x component plus square of the y component plus square of the z component. So the magnitude of vector A turns out to be 5. We calculate the magnitude of vector B, and the magnitude of vector B will be equal to under root square of the x component, which is 16, plus square of the y component, which is 9, plus square of the z component, which is 1. So the magnitude of B is 5.09. We know that A cross B we know that A cross B we know that the magnitude of A cross B is equal to the magnitude of A into the magnitude of B into sine of the angle between these two vectors. We know this particular equation. We know that the magnitude of the resultant vector A cross B will be equal to the magnitude of A into the magnitude of B into sine of the angle between these two vectors. So we simplify this equation for theta. So theta will be equal to sine inverse the magnitude of A cross B divided by AB. So we put the values in this particular equation. The magnitude of A cross B is 8.6, the magnitude of A is 5, and the magnitude of B is 5.09. So we compute the angle between these two vectors, and the angle between these two vectors comes out to be 19.7 degree. Example number 1.3. In example number 1.3, we calculate the distance between point A and point B. Point A is in the rectangular coordinate system. X is 8, Y is 6, and Z is 0. Point B is in the cylindrical coordinate system. Rho is 5, and phi is 36.8 degree, z is 0. In order to calculate the distance between these 2 points, we transform point B from cylindrical coordinate system into rectangular coordinate system. So let us transform the second point B from cylindrical coordinate system into rectangular coordinate system. So we transform B into rectangular coordinate system. We know that x is equal to rho cos phi. We know that x is equal to rho cos phi. So we put the values on the right hand side of the equation. So x turns out to be 4. We know that y is equal to rho sin phi. So we put the values on the right hand side over here, and y comes out to be 3. The z coordinate of this point is already known, which is 0. So we don't need to calculate z. So point B in the rectangular coordinate system will be equal to 4, 3, 0. Right? Now we have got 2 points. We have got 2 points. We can consider point A over here. Point A in the rectangular coordinate system is 8. Point A in the rectangular coordinate system is 8, 6, and 0. And point B is 4, 3, 0. So we can calculate, you see, the distance between these 2 points. The distance between these 2 points will be equal to under root 8 minus 4 whole square plus 6 minus 3 whole square plus 0 minus 0 whole square, and the distance between these 2 points turns out to be 5. Example number 4, find the distance between A and B. You see, this point is in the cylindrical coordinate system. This point is in the cylindrical coordinate system. Rho is 20, phi is 36.8 degree, and z is 0. So the first point is in the cylindrical coordinate system. We will transform this point from the cylindrical coordinate system into rectangular coordinate system. The second point is in the spherical coordinate system. So here is r, here is theta, and here is phi. So we transform the second point from the spherical coordinate system into rectangular coordinate system. We shall transform the first point from the cylindrical coordinate system into rectangular coordinate system, and the second point from the spherical coordinate system into rectangular coordinate system. Then we shall calculate the distance between A and B. So let us transform this first point from the cylindrical coordinate system into rectangular coordinate system. We know that x is equal to rho cos phi. Rho is 20, phi is 36.8. So x is 16. The x coordinate of this point is 16. Then we calculate y. Y will be equal to rho sin phi. Y will be equal to rho sin phi, and we know that rho is 20, phi is 36.8, so y is 12. Z is 0. We don't need to calculate the z coordinate of this point because z is already known. So we have converted this point we have transformed this point from the cylindrical coordinate system into rectangular coordinate system, and you see this is point A, which is in the rectangular coordinate system now. This is point A, which is in the rectangular coordinate system now. We transform the second point, which is B, from the spherical coordinate system into rectangular coordinate system. We know that x is equal to r sine theta cos phi. So we calculate to see x, and x is 4. We know that y is equal to r sine theta sine phi. So y is 3. We have calculated the x coordinate of point B, which is 4, the y coordinate of point B, which is 3. Let us calculate the z coordinate of this point. So the z coordinate of this point will be equal to r cos theta. Z will be equal to r cos theta. So z is 0. So we have converted this point B to the rectangular coordinate system. So the x coordinate of this point is 4, the y coordinate of this point is 3, the z coordinate of this point is 0. So we calculate the distance between these 2 points. Let us consider A. Where is A? 16, 12, 0. Okay. So A is A in rectangular coordinate system is 16, 12, and 0. So we calculate to see the distance between these 2 points. The distance between these 2 points will be equal to 16 minus 4 whole square, under root 16 minus 4 whole square, plus 12 minus 3 whole square, plus 0 minus 0 whole square. So the distance between these 2 points turns out to be 15. Example number 1.5. In example number 1.5, we have been given this vector 5ax, and this vector is in the rectangular coordinate system. We shall transform this vector from the rectangular coordinate system into cylindrical coordinate system at this particular point. You see, this point is in the cylindrical coordinate system. So this point is in the cylindrical coordinate system. Rho is 2, phi is 53.1, and z is 3. So as far as phi is concerned, here is phi, which is 53.1. So in order to transform this vector from the rectangular coordinate system into cylindrical coordinate system, we need to find out the rho component of this vector, the phi component of this vector, and the z component of this vector. So we calculate these 3 components with the help of these matrices. We have cos phi over here, sin phi over here, and then 0. We have minus sin phi over here, cos phi over here, and then 0. And in the last row, we have got 0, 0, 1. You see, the x component of A is 5. You see, A is 5ax. We have got only the x component of this vector. The y component is 0, and the z component is 0 as well. So we transform this vector from the rectangular coordinate system into the cylindrical coordinate system with the help of these equations, with the help of these matrices. So here is A. in the cylindrical coordinate system, A will be equal to 4A rho minus 3A phi plus 0 AZ. So we have transformed this vector from the rectangular coordinate system into cylindrical coordinate system. In example number 6, we have been given this vector and we want to transform this vector from the rectangular coordinate system into spherical coordinate system at this point. The point is in the spherical coordinate system. So here is R. Here is theta and here is phi. Okay, so R is 2, theta is 90 and phi is 45. Well, if we want to transform this vector from the rectangular coordinate system into spherical coordinate system, we will have to calculate AR, A theta and A phi. And we calculate AR, A theta, A phi with the help of these matrices. So in the first row, we have sin theta cos phi, sin theta sin phi cos theta. In the second row, we have cos theta cos phi, sin theta cos theta sin phi cos theta sin phi, and then sin theta. And in the third row, we have minus sin phi cos phi 0. And over here we have the x component of this vector, which is 3. We have the y component of this vector, which is 0. And we have the z component of this vector, which is 0 as well. So we put the values in these matrices. You see theta is 90 degree and phi is 45. So we put the values over here. We calculate the r, theta and phi component of this vector with the help of these matrices. You see theta is 90 and phi is 45. Alright. And we know that the x component of this vector is 3, the y component of this vector is 0, and the z component of this vector is 0. We simplify these equations. The simplification of this equation will give you this vector in the spherical coordinate system. So we obtain a two-dimensional vector in the spherical coordinate system. This is the two-dimensional vector. This vector is 2.12 AR plus 0 A theta minus 2.12 A phi. So we have transformed this vector from the rectangular coordinate system into spherical coordinate system. In example number 7, we have been given 2 points in the rectangular coordinate system. P is 2, 3, 4. The second point Q is 4, 5, 7. So we calculate the position vector RP. Here is the position vector RP. So the position vector RP will be equal to 2AX plus 3AY plus 4AZ. So this position vector is 2AX plus 3AY plus 4AZ. We calculate RQ, the position vector RQ. So definitely the position vector RQ will be equal to 4AX plus 5AY plus 7AZ. Let us consider RQ over here. RQ is 4AX plus 5AY plus 7AZ. We calculate the distance vector RPQ, and we know that the distance vector RPQ will be equal to the position vector RQ minus the position vector RP. Right? So we calculate to see this distance vector. This distance vector will be equal to 4 minus 2AX plus 5 minus 3AY plus 7 minus 4AZ. So you see this position vector is a three-dimensional sorry, this distance vector is a three-dimensional distance vector, which is 2ax plus 2ay plus 3az. Well, we calculate the unit vector in the direction of the distance vector rpq. So we need to calculate the unit vector in the direction of this distance vector rpq. We know that the unit vector in the direction of the distance vector rpq will be equal to this vector rpq divided by the magnitude of this vector. So we calculate the magnitude of this vector and we divide, you see, this vector by its magnitude. This mathematical process will give you the unit vector in the direction of the distance vector rpq. So let us calculate the magnitude of the distance vector rpq. The magnitude of the distance vector rpq will be equal to under root square of the x component plus square of the y component plus square of the z component. And then we calculate, you see, the unit vector in the direction of the distance vector rpq, and this is the unit vector in the direction of the distance vector rpq.